Good. Let's start the class today. So is the page? Can you see the page?
Yes, we can see.
Great. Okay. So so far in the class, we discussed about. So far we discussed about hardness and MP hardness in particular, and we gave 2-3 important problems, especially three partition and 3 sets, and we mentioned Hamiltonian cycle or others as well. These are the problems that you can use it to prove hardness for the problems. Here we want to go next time, like here, like I mean, in the next step, we are going and we are considering the problems which are in P. This is the one that is called fine-grained complexity. The idea is that for the problems in P, now we would like to see the classes of the problem that we can solve. So what are the important problems in this? Let me just so we have this class P, of course. Then in the class P, we have this, I think I mentioned it, this is N, the running time of those algorithms which are order N. Order N, in some sense, generally seems the optimum solution, unless you don't want to see or read the whole input. There are some cases like local algorithms or others that you may only read a constant number of inputs at random, but generally those they are probabilistic and you don't get the exact answer. Often if you want to get the exact answer, you need to at least read the input, because if there is some part of the input which is not necessary, then you can maybe remove them. So it's not necessarily something that you want to do it. Because of this, I mean, order N is somehow seems that like the optimum that we can do. Then the next one that is coming, it is order N square. These are the set of problems that we will talk about them, especially 2 problems here. It is a 3-sum that we talk, next time. And the other one is the, this is called a perpendicular vector problem. Perpendicular vector. Vector. So these are the 2 famous problems that there is a N square algorithm for that, and we don't know whether there exists anything better. So in the 3-sum that we will define next time, we are given a list of numbers, N numbers, and you want to see whether there are 3 numbers that may include a repetition of one number itself, such that the sum is equal to 0. In the perpendicular vector problem, you have N vectors are given to you, and N vectors, and the size of these vectors, so the size of them is actually order log N. And you want to see whether there are 2 vectors such that they are perpendicular to each other. It means that if you just multiply them, like the inner product, that would be 0. So this is the second problem. These are the 2 famous problems that several hardness results are coming. What's the meaning of hardness here? It means that you want to say that if you will create a set of problems, again, the same thing that we had it, for example, for MP completeness, a set of problems that if you solve any of them, better than n square, then you can solve all of them in n square. So we try to create such kind of classes. The other problem that is now in after that, it is n to the 3 or cubic. That's the one that we are talking today. So these are the problems, like especially all pair shortest path is a famous problem that in this category that we try to talk about. So these are the problems that for them we know n square, in cube algorithms, but we don't know anything better than that. And this is again a major problem to see whether we can find any things better than n cube for these problems. So that would be all pair shortest path and several related problems that we will discuss in this. And I mean, after that, I think for n to the 4 or something, there might be some problems, but they are not that exciting because already this n, when n becomes large, is so huge that the people may not, I mean, care that much. You can create some problems also, like some generalization of 3 sum. You can say, I don't know, 5 sum or something like this, or that are also n square. But these two classes especially are very important. That the fine-grained complexity is talking about these two classes, that whether we can get from n square a little bit better or from n cube a little bit better. Does it make sense? Any questions? Great. So let's discuss. So today we want to talk more about this all pair shortest path and see what are the results there, what are the hardness there. This one of the we are not discussing that much about n to the 4, but you may actually do this one as a, I mean, search more about it and see whether there is anything there or not. Great. So, so what is the all pair shortest path? Let me first define this one. So you are given a distance xy. So this is the distance xy. So this is the matrix that are given, that for any x and y, I mean, you want, okay, so this is in some sense the input and the output. So what is the output? You want to, for each x and y, you want to compute what is the shortest path between x and y in a given graph. But then what is the graph? The graph itself is, you can consider it's given as a matrix to you. So this is some kind of is a matrix, the adjacency matrix, for example, that here you will say for ij, what is the, this is the weight of the edge or the length of the edge. So this is the length, this is the input. And this is the output. So you can also consider, I mean, the input can be given as the adjacency matrix, or it can be that you can consider it when the simplest things, that we have an n node m edges graph. And here we have the list of edges is given. Is given. However, these two actually are not that important, like adjacency matrix that we talk about here. Versus this type of things that the set of edges is given to us. Why did there is not much difference in this case? Please unmute and answer. So the answer actually is this one, because here we are talking about an order n square on n to the 3 cube. So in that case, if you get the list of the edges, you can turn it in, say, in order n square. You can create this adjacency matrix. Or vice versa, if you have this adjacency matrix, then you can get in order n square, you can get the set of all edges, because you will read everything. So because here the problem is actually, we are talking about n to the 3 and improving over n to the 3, then n to the 2 operation is not, is not, doesn't have any issues. That's the reason that actually we talk about it, we call it order, here we are talking about like n to the 3 epsilon, that we call it subcubic. We call it subcubic reductions. So here the goal is to get, whether for this n to the 3, for the all pair shortest path, that I will mention the algorithm as well. The question is that, can we get anything better than n to the 3? And so here, to do so, if there is some two problems, that you can do some operations with something in a little o of n to the 3, like n to the 3 minus epsilon for some constant epsilon, we call it subcubic, then such a reduction is fine for us. And we can do all these operations. The only thing that is important for us is breaking this n to the 3. And yes, so in that case, adjacency matrix or adjacency, or the given set of edges, there is not much difference. And here, this is an important one. And we are assuming that given directed or undirected, either in form of adjacency matrix or in the set of edges, such that the weights are between 0 to m. So the edge weights are between 0 to some number m. In this case, we are considering all positive case. So here we consider the positive case. And now, what is the algorithm n square n to the 3? N to the 3 is one of the probably the simplest algorithms that we have it in graph. So essentially, it is just 3 loops inside each other. So we say for I is equal to 1 to n. This is the algorithm which is called a Floyd-Warshall. So for I is equal to 1 to n, then the other one is for j equal to 1 to n. And the last one is for k equal to 1 to n. So this is the thing, the only thing that we say that if distance of j and k is less than or equal to distance of j and I plus distance of I and k, distance of I and k Then update. So here it updates distance of J and K. Good. So this is the Floyd and Warshall algorithm, that inside F4 we have a 3, 4, I equal to 1 to I equal to just also let me do this test as well. One thing I wanted to yeah. So let me just great. Yeah, so that is the one that I wanted to actually check it. So this is exactly the same algorithm. You can find it in Geek for Geeks. We need to log in essentially. So here the algorithm that is also mentioned in Geek for Geeks. Okay, so coming back here, why did I want to check that one? This is the important one. This order is very important. Maybe actually I can just even decrease this one. Now you can see it actually better. So this is the one that you can see better. So here we have the 4, I equal to 1, j equal to 1, and k equal to, like, from 1 to n. Here we talk about the distance of jk. And jk is very important here. So jk is these two variables, j and k, the inside variables. If their distance is this distance distance between j and k is sorry, that should be actually greater than or equal. If the distance, of course, because of the triangle inequality, we know that the distance from j to k should be less than or equal to distance from j to I and then from I to k. So if it is not the case, then update the distance jk to this minimum, to this lesser amount. And here it is very important that we are talking about j and k. So the order of these loops and the variables that you will put in. So this is distance j and k. And the I should be the outside variables, that here would be the middle vertex. This is very important. This middle vertex should be the one that comes first in the loop. It's a very simple algorithm. I have implemented, I don't know how many times this one. And it is super important that you will have the order, and the middle guy that here you want to find kind of pivot out of it, that should be the variable of the first loop, not the other ones. Actually, if you don't do that, this is one of the main source of problems, that you may write a program and then you have an error and you don't understand what is the problem, and this is the problem. Because here, how does it work? The idea is that you want to say that this is an induction on I. So the proof is actually induction on I. That's why this algorithm, all pair shortest path. So it is very important that I is coming first, and we are doing induction on I. And we say that when we are saying the first I vertices, the distance between these guys that could use all of these vertices, we have the best such a distance, or the best such a shortest path stored in the distance j and k. So it is important that the I comes first, and then j and k are coming, and this j and k goes through all vertices of the graph. This simple algorithm, this 4 exactly, there is 3, 4, and this simple operation that if distance of j and k is greater than the distance of j to I and then I to k, then just update the distance jk with this lesser amount. This is the n to the 3 algorithm that we have it for all pair shortest paths. And this, at the end, the distance matrix, this is the distance matrix, is the one that we talk here. That's the one that stores the shortest path. And that's the best algorithm that we have it. So I don't know how many years ago this algorithm has been developed, probably 50, 60 years ago, if not more. But that's currently the state-of-the-art algorithm for all pair shortest paths, that you want to find the distance between any two vertices in the graph. Is the problem clear and the solution clear, the one that I have mentioned? So just some voting. How many of you actually have implemented this Floyd-Warshall algorithm? Just, I mean, raise your hands. So no one has implemented this all pair shortest path algorithm?
Sorry, I don't know how should I raise my hand in the Zoom.
Okay, so you can actually go to this one, the actions. I think you can do the, so you have done it, correct, Ali?
Yes.
I have also implemented.
Yeah, okay. So this is actually a very important algorithm. It's like, as I mentioned, it's like the simplest algorithm, and we don't know anything better than this 3 4s inside each other. And that's the whole, we are now creating a whole class of problems that, in some sense, the best thing that we can do is this 4 inside each other. There is no other way that we can do it anything smarter than this. Good. Now let me clear everything. And then let me maximize this. Good. This is the problem, all pair shortest path, that we discussed, and the hardness of these problems. Now, we are talking a set of other problems that also these are hard problems, and we can actually see the reduction between. So what is the radius of a graph? So what is the radius? So the radius of a graph is the minimum over all v, maximum distance from this. So when we compute this distance xy, for each distance, vu essentially means what is the length of the shortest path between vu. So that is the length of the shortest path. Length of shortest path. Good. So when we have this distance of length of the shortest path, so here what does it mean? So the radius is like, we can consider, we need to find the essentially a vertex v, which is called the center of the graph, such that the distance of any other vertex, so this is, we want to minimize this radius. To minimize this radius. This is the radius. You will go over all vertices such that each other vertex is reachable to v at the minimum distance. You will consider over all v, and you will find that this quantity is minimized. And that will be the radius, and this v is called the center. Is the definition clear? Please unmute and answer.
Yes, it's clear.
Great. So this is the radius. The other things that we are talking about is the median. What is median? The median is essentially the same, very similar things. Again, you will consider over all vertices, but here, instead of considering the max distance, you will sum the distances. So consider this vertex v, and then for each vertex, you will consider this guy and then take the sum of this. And you want to find a vertex V that minimize this one. You can say this is the, when generally we talk about the center, we talk about the center of radius. But you can consider center for median is the vertex that has this property. Now, and one important thing, if you work in the algorithm design, there are these two concepts that generally very important: max versus sum. But actually, for the sum, I can say also slash average. So almost any problem that you want to consider, this is actually a nice way of solving or finding problem. If somebody solves this problem for the max version, generally also the sum version or the average version is interesting. By the way, sum and average are the same. You see, the quantity that we have it here, you want to consider minimum V over all U, that the distance of UV. We can actually divide everything here. You can divide everything here by n as well. Say n is the number of vertices. So that does not change the optimization problem. Why? Because this n is the same for all vertices. But if you do it for all vertices, if you like sum it divided by n, where n is the set of all vertices, in this case, this would be the average distance from the average distance of any vertex from V. So this division by n happens in lots of problems. Generally, sum and average problems are the same, and the max is another version. And this is a very typical thing that if somebody solves the problem for, say, for sum or max, then you can also, this is a very important thing to get it for max, or if you get it for max, you can get it for sum and average. And generally, both of them are interesting. So the approach that is worked for sum and average is not necessarily worked for max, and vice versa. This is very important. These two, they often need different techniques essentially to get a nice result. So they seem very similar to each other, but the techniques and the results are often different for this. Like for example, for one problem, we have a 2 approximation for this, but the approximation for the other one might be 3 approximation and using a different approach, or vice versa. So always, and I will say, actually, this max version often is a bit harder than sum version. So max is often a little bit harder than the sum version, sum or average version. And again, this is something that you can consider it in your research. Just go, any problem that somebody consider sum, you may consider the max, and or vice versa. Great. Now, so we discussed about this max and sum, and this is the center that we talk about it. Now, what is the diameter? The diameter, so in some sense, the radius is the one that is like you will find the center such that each person is reachable from this. So the diameter now is the maximum distance between any two vertices in the graph. So you are given a graph, and you want to say what are the extreme cases that between U and V, the distance of U and V is maximized. So this is the max U and V, distance of U and V. So this actually have applications, these measures that we are talking about have applications in lots of cases, like in social network, on transportation, on computer and biological networks. These are the most famous problem in the whole system. We discussed about the Floyd-Warshall algorithm for n to the 3, that we can actually solve the problem in n to the 3. There is another way also that you can do it. This is using the Dijkstra algorithm. What is the Dijkstra algorithm? So Dijkstra algorithm, it is called Dijkstra. So what is the Dijkstra algorithm? This is also called a single source shortest path. So so what is this single source shortest path? So here you are given a vertex V, and you want to find all shortest paths, like from any vertex to vertex V. So this is the shortest path from all vertices to a vertex V. It is different from all pair shortest path. In all pair shortest path, we want to find the shortest path between any two vertices. Here we want to find the shortest path from vertex V to everyone. I mean, say the graph is undirected, for example. It works also for directed graph. But so this is the one. And the running time of this algorithm, actually, this one that we can get it, the running time is of the Dijkstra algorithm is order m, the number of edges, plus n log n. So this is the Dijkstra algorithm that we can actually have it. And so how can we get the all pair shortest path from the Dijkstra algorithm? Please unmute and answer.
Iterate on all vertices.
Yeah, go ahead.
Iterate on all vertices and run Dijkstra from.
Exactly. So you can iterate over all vertices and just iterate for this Dijkstra algorithm, and the running time would be n times that. So n times these things, which would be mn. This is the running time essentially. Mn plus n to the 2 log n. But here mn, so of course m in the worst case can be n squared, the number of edges, times n would be n to the 3. So in some sense, this algorithm, if m is a small, so when we have it, we have here mn, this is n squared. So this algorithm, if m is a less than n squared, or is a sub square, so in that case, subquadratic actually, if a subquadratic, then this would be better algorithm because it is m times n. But in the worst case, that the graph is dense and m is also omega of n squared, then this becomes n squared as well. And again, there is no algorithm better. So there are some algorithms, some other things, but at the worst case, again, it is n squared. The question is that now, can we get anything better than n squared? Sorry, n cube. And the first such result was obtained by Friedman in 1976. So the old things. He got n to the 3 times square root of log n, the third root of log n, over square root of log n, third root of log n. So this is less than log n, of course. So this is a little bit better than n to the 3. So there is also a better algorithm. This is obtained by Williams in Ryan Williams in 2014. The running time of this algorithm is n to the 3 over 2 to the square root of log n. Generally, this is also important thing that I have mentioned. We are working with these guys. I mentioned we have order 1. Then we have something like log. So this is a class of problem that we are talking about, or approximation, or I don't know, running time, etc. So this is order 1 constant. Then log n. I mean, sometimes we consider it log star. What is log star? Log star of n is the number of logs that you need to get it from n such that it becomes less than 1. So this is order 1. This is log star n. Log star n is very a slow growing function. Even log n is very slow growing. Even log n relatively is not bad. It's a slow growing. So we have, we have actually before that, we have also a square root of log n. So we have order 1, we have log star n, then we have log n, then we have a square root of log n. And these are the bounds that the people obtain for different problems. So this might be some other, I don't know, maybe the root 2 is a natural one, but maybe even have root 3. Then you will have log n. Then, of course, you have log n to the 2, or you have a polylog in general. Then after the polylog is this one, is 2 to the square root of log n. Note that this 2 to the square root of log n is actually not equal to a square root of n. So after this 2 to the, so if, of course, if we are putting the square root over everything, it would be 2 to the log n square, which is 2 to the, which would be a square root of n. But the 2 to the square root of log n is something between polylog and actually maybe more generally, it is n to the epsilon for some constant epsilon. So it is something between these two important things, polylog and n to the epsilon. And then after that, we have like n to the epsilon in general, maybe a square root of n, and then we have order n. Sometimes order n squared or n cubed, and so on and so forth. So this is the set of important, set of important bonds. That is, and this is very important. So when you are, again, working on any problems, if some of this, somebody has obtained any of them, say, for example, if you obtained log n, actually, there is one other thing, maybe I can just put it here. This is also a good one here in between these guys. And this would be log n over log n. So these are a set of, very natural bonds that if somebody has obtained one bond, in any area that you are working, the question is that can you go a little bit lower and get one lower ones? And these are, I think that's a very good one to memorize, that if somebody obtained log n, then the question is that can you get log n over log n, or even third root of log n, or second root of log n, or just square root of log n, or log n, or log star n, or order one. So this is the one that is almost never ending. If somebody obtains any bond for this problem, the question is that can we do a little bit better than that, or there's a lower one. And in this case, it is especially important, this bond, as I mentioned. If you see the bond of Williams is like this, 2 to the square root of log n. So this is this bond. And the question is that whether you can improve it a little bit to n to the epsilon. Because if we can improve it a little bit to the n to the epsilon, then the running time of this would be n to the 3 minus epsilon. And that's exactly the main open question that we have, the big open problem, that whether there is a truly subcubic algorithm, which is n to the 3 minus epsilon for some constant epsilon for all pair shortest path. And you will see that this log n over this one, these are like earlier in this category if you inverse it. And then it has been there, and then Williams obtained, so sometimes here still is polylog version, these bonds that are, or 1 over polylog. But here he obtains 2 to the square root of, the denominator is 2 to the square root of log n, this bond. And the question is that can you go a little bit more and you get it n to the epsilon? That's a big open problem. And actually the conjecture is that this one is that for any epsilon greater than 0, you need n to the 3 minus epsilon. In some sense, you want to say that n to the 3 is something that you cannot do anything better than that. For this problem, for any epsilon, there is no constant epsilon that you can get n to the 3 minus epsilon. For any epsilon, still it requires this one, and we cannot get n to the 3 minus epsilon. Good. So is it clear so far? The hierarchy is the set of important bonds that I have mentioned. Again, these are for general research. So any research that you are working on, any problem, probably you will deal with some of these functions. And the question is that whether it is tight or you can do a little bit better than that. Good? Clear? Good. So let me clear everything again. Good. Good. So we discussed that one. Now the question is that good. So this is the main question that we have it. This is a conjecture that we don't have any proof for that. Now, one other important thing, when we solve the all pair shortest path problem, if we are paying this order n to the 3 to find this, solve this problem, after that, all of these other problems that we discussed, like radius, median, or diameter, they will be easy. And they only need order n square time. Why? For example, if we have this final distance matrix, so this is a distance matrix. Why can we solve? So say we are paying n to the 3 and we are finding the distance between any two vertices. Then why can we solve radius problem in order n square? This unmuted answer. Why can't we solve this problem in n square? So please unmute and answer.
For every vertex, you need to know the most distant vertex. So it's an O of n, and we have, if we iterate on all of them, it will be n squared.
Yeah, exactly. I mean, say, for example, for radius, if you want to solve the problem, what do? You will iterate over all vertices here. So you will iterate over all vertices here. And for each vertex, you will see who is the max guy. And then you will, among all of these guys, you are choosing the one that the maximum is higher. So if this is the guy, then this would be the radius. The same thing you can do for median, because median, you are just sum it up over all vertices. So you will just sum it up over all vertices, and you will get it. Of course, for diameter also, you just go through this matrix. So in some sense, when you have this matrix computed, then you just go through it once, and then you have all these measures, radius, median, or diameter. These things that we are talking, radius, median, diameter, they call them centrality measures. So because they are saying, I mean, how central, essentially, radius, median, or diameter, they say that somehow they are measuring centrality. The one important thing that if we have all pair shortest path, so we had all pair shortest path, then we can compute all of these problems in n square. The question is that can we do any of them better than n to the cube? Because yes, if we have n cube for all pair shortest path, then we can solve them in order n square. But can we do something without all pair shortest path such that the running time is still better than n cube? And note that because first you need to do all pair shortest path, the running time of all of this algorithm would be still n cube using this way. Is there any other way that we can get subcubic algorithms? And the answer is not really. So for these problems, except diameter, so for radius and median that we will talk, except diameter is still the big open problem. So for diameter, we don't know whether you can do it like essentially n to the 3 minus epsilon. We don't know for diameter that whether such an algorithm exists or not. This is a very big open problem here. But the radius and median and others, you can show that actually for them you need all pair shortest path. You cannot do it also better than n to the 3 if all pair shortest path, you cannot do it better than n to the 3. So in some sense, for radius and median, the only or the best way is to just find the all pairs and then compute this radius and median. And these are the results in Abbott et al. In 2014. And the question is that, of course, I mean, this can we compute them in truly subcubic time? And in this case, as I mentioned, especially for these two problems, radius and median, we can say that they can be solved in better than subcubic time, in subcubic time, if and only if all pair shortest path can be. So we talk more about it. But again, for diameter, we don't know the answer. For diameter, of course, if there is all pair shortest path is given to us, we can compute it in then we can compute it in quadratic time with total cubic time. But can we do anything better? That's the main open problem. So before going to some of this proof, let's define also another definition, the betweenness centrality. This is also important. So what is the betweenness centrality for a vertex V? So the betweenness thing for a vertex V is the fraction of shortest path of ST paths that using V. So consider this is vertex V. The question is that for how many vertices, like if you consider the shortest path between any two vertices, I mean, just for any two vertices, say what is the shortest path between them? So this is, so the question is that here, for example, one of the shortest paths between these two guys, so this is actually the computing for all pairs. So for all pairs of vertices, for all S and T, if you consider this one, for example, if this is S and T, and this is all pair shortest paths that is going there. So maybe there are two things and two shortest paths, and one of them goes through V. In this case, BST of V would be half. And then you will compute this over all ST vertices, all pairs, and see how this guy is a central. That's the thing. How this guy is a between the short, like betweenness means that how this guy is central is in a sense that is a hub essentially for shortest path. Now, if all pair, so if here we are assuming that maybe for this S and T, there are two shortest paths that they have the same time, same essentially length. If we are assuming that all shortest paths are unique, so and that is not hard to do that. If you are disturbing, if you disturb each edge, E, the weight of or the length of each edge, E, it's a little bit random noise. Then actually we can get it that the shortest path between any two vertices should be unique. Now, if the shortest path between two vertices are unique, then the BCV of this guy, what is the BC of V? The number of ST pairs that with the shortest path passing through V. Because in this case, then we don't have two options here and here. We have only one option. Then you will go, what is the BC of V? Then you consider V for any vertex V over all these guys. See whether, just count the number of pairs ST such that their unique shortest path is going through vertex B. In this case, here the number of ST pairs that the shortest path goes through B, it is called BC of B. So this is the betweenness things that we are talking about it, in a sense that for how many vertices the shortest path between them, unique shortest path goes through. And finally, this is the concept of subcubic reduction from A to B that we discussed. So assuming an algorithm of truly subcubic for B, can we obtain an algorithm of truly subcubic for A? So again, here, we want to, when there's this reduction from A to B, we want to solve A. So we want to solve A using B. So if for B there is a subcubic, can we solve also for A subcubic? That is the one that is called subcubic reductions. And we are talking about lots of subcubic reductions here because in some sense, subcubic does not change the complexity class of like cubic algorithms or n to the 3. So as long as you have subcubic, if the problem is, we believe that it is n to the 3 hard, then it still remains, the new problem also will be n to the 3 hard. Any questions? Is everything clear? Okay. So we talk about these things. Now let's go to the next page. So this is the so this is the current state of the art that we have it. For these problems. So the main theorem is this one: the radius, median, and betweenness centrality all subcubically equivalent. And they are actually equivalent of all pair shortest path as well. So this is the median, radius, and betweenness centrality. So all of these problems are subcubically equivalent. It means that if you can solve any of these problems better than n to the 3, then you can solve all other problems. And note that all of these guys, the radius, all pair shortest path, median, or betweenness, the main goal is to find, like, for example, what is the radius amount. But if you want to find the vertex, the center, also you can do it. You can do some kind of binary search and others do it. But in the current forms, these are the ones that you want to see whether, what is the radius, what is the median, what is the all pair shortest path, actually you want to find all pairs. But all others betweenness, these are just some number you want to compute. And a majority of these results are from this paper of Abod et al. In Soda 2005 that we talk about. So what is this problem? This is the reduction, essentially, that this is the one that some of them are like easy, trivial, and some of them are non-trivial. For example, as I mentioned, if you have all pair shortest path, using all pair shortest path, you can solve diameter. So that we know that. Or here again, if you have all pair shortest path, you can solve radius or median or others. These are some of them are non-trivial. This is the main open problem. Whether if you can solve diameter, can you find all pair shortest path? That we don't know. But for other problems, we know that, for example, for radius or, for example, median or betweenness centrality, if you can compute this, then actually you can compute all pair shortest paths. So that's actually is a very interesting problems that these guys, and this actually goes through this negative triangle. That this negative triangle, I will define it, but yeah, and for diameter there is another one called positive betweenness. So positive betweenness, we talk about the BC of V, so betweenness of V. The question is that whether there is how many shortest paths are going through V. The positive betweenness, this is the problem that asks whether for a vertex V, whether this number is greater than 0 or not. So the question is that are there two vertices S and T such that the shortest path between them goes through V or not? That's essentially this problem, the positive betweenness problem. And we know that the positive betweenness is equivalent of diameter. But we don't know whether, but still we don't know the relation. So diameter and positive betweenness, it seems they are equivalent, but the relation between all pair shortest paths and diameter, we don't know. As I mentioned, for other problems like radius, median, and others, we know that if they can solve better than in cube, then we can solve also all pair shortest paths better than that. So in some sense, they are equivalent. This is the definition of positive betweenness that I have mentioned. Determine whether some shortest path uses a vertex V or not as an intermediate node.
Question?
Yes.
Isn't positive betweenness centrality easier than betweenness centrality? At most as hard as betweenness centrality, because if you have a solution.
Yeah. Of course, I mean that is trivial because if you know what is if you can compute the betweenness of a vertex, then you can it is greater than 0 or not.
Yeah. So, but in this diagram, why is this equivalent to diameter and not like on the left hand side, not equivalent to APSP?
As I mentioned, so positive betweenness is easier than betweenness in some sense.
So which means that diameter is easier than, for instance, radius, right? Because these problems.
So I will say, let me say correctly. A positive betweenness maybe is easier than betweenness centrality, but definitely not harder. Because if you compute the betweenness, then you can compute that.
So from this diagram, can we conclude that diameter is at most as hard as radius? Because diameter is, you're saying, is equivalent to.
Yeah. You can get that. Yes, exactly. So in some sense, radius and medians are harder problem than diameter or betweenness centrality.
Okay.
Yeah. So all these problems are harder than these problems. We don't know whether they are equal, just greater or greater.
Okay.
Clear? Now, one important problem is this one. What about the approximate solution? So somebody says, okay, maybe these are the problems. These are all for the exact thing. What about for approximate solution? Can we do, like for this problem, can we do approximation better than like in subcubic time, in truly subcubic time? And here we talk about, again, truly, because why we say truly? Because already there is n to the 3 to the square root of log n. So this is, in some sense, this is a subcubic, but it's not truly, because the truly would be n to the 3 minus epsilon for some constant epsilon. So that would be truly one. This would be just, most of them are subcubic, but this one is a truly one. Okay, now what about approximations? Good. So for approximation, what do we know? So actually we can, for all pair shortest path, we can compute this one in this running time, n to the omega over epsilon. So we can so for any small constant epsilon, we can compute it in order n to the omega over epsilon. What is omega? Omega is actually this number, 2.37, something like this. This is the best running time that we have for matrix multiplication. So if you have n by n matrices, how can we multiply this one? The best running time for this guy, a naive way would be essentially all pair shortest path, because you are going through every row of this guy and every column of this, and you will multiply, and that would be order n to the 3. There is a Strassen algorithm that you can actually do it better than n to the 3, and currently the best one for this problem is n to the 2.37. This is a very important one. What is the best one for this? Still, we don't know, but we know it is substantially better than 3, 2.37. So if you want to get approximate 1 plus epsilon, then actually you can do much better. I mean, you can do it at least subcubic time. And we don't know what is this exact W is there, but so we can do it better than that. And so in some sense, the problem becomes really hard when you want to get the exact. You don't want to essentially don't want to lose anything. This is the best fast matrix implication. This is the one in the Algorithmic paper. So so it is interesting. This gives actually subcubic p-tasses for radius and median. Because of course, if you have this 1 plus epsilon for these two problems, then you can get these results for radius and median, because you are losing again the 1 plus epsilon there, but does not help for betweenness centrality, things that I have mentioned. Because there actually you want to see whether there is a shortest path which is going to that, and that's not much thing essentially. So indeed there is such a hardness result. What is this hardness result? It says that if you have 3/2 approximation of diameter or a betweenness, so the betweenness problem, essentially the one that we talk about, whether like how many vertices, how many shortest path goes through this vertex. If there is a 3/2 approximation of diameter in order m to the 2 minus epsilon, m is the number of vertices, then in this case means that the set, so set is the strong ETH. This would be false. What is the strong ETH? So first you need to know, okay, so this is a strong ETH. What is a strong ETH? It says that essentially for the SAT problem or the 3-SAT problem on n variables, the best thing that you can do it is 2 to the n. So how can we solve a SAT problem in 2 to the n time? Please unmute and answer. So how can we solve an n variable SAT in 2 to the n time? So that's easy actually. I mean, just try all variables. There are all v1, v2 to vn. Just consider all possibility and say whether they are true or false. And then this is 2 to the n essentially. So a strong ETH. So ETH is this one, and then a strong ETH says that actually this is the best that you can do it. You cannot do it 2 to the minus epsilon to the n for any constant epsilon. So you cannot solve this problem in 1.9999 to the n for 3-SAT or SAT in general. And this is equivalent of this. So you cannot solve this problem in 2 to the essentially delta n, or I don't know, sigma n actually, for any sigma or delta less than 1. These two are equivalent. 2 minus epsilon to the n and 2 to the this one, I mean to the sigma n for some sigma less than 1. Good. So these two problems are somehow equivalent. Now, what is this is a strong, this S is a strong. What about ETH? So ETH it says that it's a bit weaker. It says that we cannot solve SAT in 2 to the little o of n. So this is the little o. So a strong one say that even the constant should be essentially 2. You cannot do 2 minus epsilon. This guy said maybe you can get a constant a little bit better than 2, but still it would be linear in n. Maybe 2 to the, I don't know, 2 to the 1 point, like, I don't know, 2 maybe n over log n. So set essentially, so this is a strong ETH. And this is ETH. So this is ETH and this is a strong ETH. A strong ETH says that the constant even should be, I mean, you cannot get anything better than like 2 to the n, essentially. Here it says maybe you can get 2 to the, I don't know, 1.99, like 0.999. But you cannot get something like 2 to the n over log n. That is not possible. This is ETH, this is strong. Anyhow, this one says that 3/2 approximation of diameter. So if you want to get, essentially, if you can get 3/2, 3 point, like if you get 1.5 approximation of diameter and betweenness in m to the 2 minus epsilon. So if you can do a little bit better than, like m is the number of edges to the 2 minus epsilon, then, and this is for general graphs. So for any graph M, then it implies that actually set is false. Anyhow, this is some approximation results. And the main open problems here is this one. Can we get similar approximation results for, like, especially to this theorem, for radius or median? That we don't know. And of course, the main open problem is that whether diameter is equivalent to all pair shortest paths under subcubic time or not. So getting such kind of result for approximation is important, as well as this getting this all pair shortest path, finding the relation between all pair shortest path and diameter. Any questions? Good. So, okay, so there is this problem of negative triangle that actually I can just that plays a very important role here, as you will see. This negative triangle, but that actually we will talk more about it next time. So about the negative triangle, we will talk more next time. And we are proving some of these results. So next time we are defining this one, and we are negative triangles, and then we are proving some of this relation that exists. We are talking about them and we prove them. I mean, you can get the actual things in this paper, this Soda paper, and also the I think we mentioned them in the book, but the more complete version would be in Soda 2015 by these guys. But we will talk some of them, such as you will see how do they get it. These are actually very cute type of reductions that you can get it. And the whole idea is that whether for this problem n to the 3 is the right answer, or running time, or something better than n to the 3. And again, the main important problem is this question mark, the relation between diameter and all pair shortest path. Whether diameter is as hard as all pair shortest path, or we can do something better for that. Any questions? Any questions? Okay, so if there's nothing, then we can finish this one. And yeah, just work on the projects and presentations. So talk to you in the next session. Bye for now.